Ethernet is the most popular local area networking standard used to transmit data between devices. In this video, we're going to talk about what makes the Ethernet architecture unique. Let's start by looking at the different Ethernet topologies. Ethernet can be used on one of two physical topologies, bus or star. Older Ethernet standards used a physical bus topology where you had a single common half-duplex trunk, also called a bus, that all network devices connected to. If you encounter this topology, it's important that each end of the bus is terminated, which prevents the signals from reflecting off the end of the transmission line. In a physical bus topology where one computer sends data to another computer, all the computers process the data and analyze it to see if it's intended for them. Basically, the message is broadcast down the bus. The Ethernet bus topology has several advantages. For example, it's very easy to connect a computer or other devices to a bus cable. And since all the devices are connected to the same linear cable, the network uses less cable than other star topologies. This means it costs less to implement. It's also very easy to expand, making it ideal for smaller networks. Ethernet bus topologies do have a few disadvantages though. Since all devices use the same medium for data transmission, there's a high probability that two devices will transmit data at the same time, resulting in a collision. This causes packet loss and the need to retransmit the lost data. The use of a single bus line also means that network performance is degraded as more devices are added to the network. Another major concern with a bus topology is that if the cable is broken or severed, the whole network goes down, and troubleshooting the location of the break can be very difficult to pinpoint. Because of the challenges associated with a bus topology, most networks today use a physical star topology where every device is connected to a central device, such as a hub or switch. Ethernet architectures that use a physical star topology can use one of two logical topologies. Hub-based networks, although configured physically like a star, use a logical bus topology. This means that when a signal comes into the hub, it's broadcast to all other devices on the network, similar to what happens with a physical bus topology. Switch-based networks use a logical star topology. This means that when a signal is sent to one device, it's forwarded only to that device and not to any others. In other words, the switch virtually eliminates broadcasts and instead sends directed communications to the intended device. When it comes to the physical connection of your devices, Ethernet supports both copper coaxial and copper unshielded twisted pair cabling, as well as fiber optic cabling. Ethernet uses a unique media access method, which is a set of rules that determine how devices can access the network medium and transmit data. This is known as Carrier Sense Multiple Access Collision Detection, or CSMA-CD. Let's look at how this works. In this scenario, we'll use a linear physical bus topology, which is also used in a logical bus topology. Computers A, B, and C are connected to the network medium. Suppose computer A needs to send a message to computer B. According to the CSMA-CD media access method, the first thing computer A must do is listen to the transmission medium to see if data is already being transmitted. This is what we mean by carrier sense. It's like using a two-way radio. Before you talk, you briefly listen to see if anybody else is already talking. Let's say that computer A listens to the medium and determines that it's clear, so it transmits its message to computer B. Computer B hears the message and sees that it's something it should process. But because you're using a bus topology, at the same time the message is sent to computer B, it also continues down the wire and arrives at computer C. But computer C realizes the message isn't for it, so it discards the message. Now, let's suppose that computer C has a message to send to computer B. It'd go through the same process. First, it listens to the medium to determine if it's busy, but this time computer A is in the middle of a transmission. Computer C can tell that a signal is being transmitted on the wire, so it waits for a random period of time. While it waits, computer A finishes its transmission. Computer C then listens again, and hearing that the transmission medium is now clear, it transmits the message to computer B. Suppose now that both computer A and computer C have a message, they want to send at exactly the same time. They each listen to the transmission medium, determine that it's free, and then transmit simultaneously. This creates a collision. That's when two messages are sent at the same time by different hosts, and the signals collide. In the end, computer B never receives the information. At this point, computer A and computer C stop transmitting their frame, and transmit a jam signal to inform all hosts that a collision has occurred. After the jam signal, the devices perform a backoff, where they each wait a random amount of time before starting the process all over again. Because the backup time is random, one of them should back off a little longer than the other, so when they retry, the likelihood of another collision is decreased. As we mentioned earlier, the CSMA CD media access method is designed to work on a logical bus topology, either on a physical bus with a logical bus, or on a physical star with a logical bus. As the number of devices on a network increases, so does the number of collisions. With a very large number of devices, your network's transmission speed and bandwidth degrades significantly because of the increase in collisions. You can eliminate the collision problem by simply using a switch instead of a hub. A switch offers a guaranteed transmission path between two connected devices. This network here has 4 devices connected through a switch. So when one device needs to send a message, logical circuits inside the switch isolate the network traffic and send that message to only the destination device. A switch can also simultaneously send multiple messages. For example, we have a dedicated path through the switch between these 2 computers, yet these 2 devices can also establish a dedicated path for communication. And because the communication path is used only between the 2 devices and no others, collisions are eliminated. Without collisions, there's no need for carrier sense or collision detection. As soon as devices are ready to transmit, they simply transmit. They also don't try to sense collisions. When you use a switch, the media access method doesn't apply. It's still there in the specifications, but the devices don't need it. Switched Ethernet networks are much faster than hub-based ones because even if you add more devices, the number of collisions remain at 0. This allows for much larger, more efficient network segments. Duplexing is also an issue. If you use a hub, all devices connected to the hub share the same transmission media. Because of this, you need to use half-duplex communication. This means that all devices can either transmit or receive, but not at the same time, kind of like a walkie-talkie or CB radio. When you use a switch, you can use full duplex communication, which allows hosts to transmit and receive data at the same time, like a phone call. Full duplex provides double the bandwidth of half-duplex communication. Now that we've learned about how packets are transmitted, let's see what's actually in a packet. A packet being sent between devices contains the destination and source machine's IP addresses, as well as the data to be transferred. Ethernet encapsulates this packet within a frame. The first part of the frame is called the preamble. It contains a series of zeros and ones that alternate as 01, 01, 01. The preamble identifies the start of a frame and informs devices that everything that comes afterwards is part of that frame. The preamble always ends in 1, 1, which signals that it's ending and the rest of the frame is starting. Next, there's the destination device's MAC address, followed by the source device's MAC address. Following the MAC addresses is the payload, which contains the packet it received from the network layer above it. An Ethernet packet's data portion is set to a fixed size between 64 and 1518 bytes. If the data is smaller than the specified size, the unused space in the frame is filled with padding. Within this portion, you have the data followed by enough zeros and ones to bring the size up to the standard. Ethernet devices detect collisions by identifying frames that are smaller than the specified size. When a collision occurs, it's likely that the fragments left over are much smaller than the minimum size. This signals to devices on the network that a collision has occurred. The last part of the frame is the cyclic redundancy check field, or CRC field. The CRC contains a mathematical computation that's performed on the frame information before it's transmitted. If the CRC computed on the destination host matches the value in this field, we know the data arrived intact. If something happened to the frame during transmission, the CRC calculation on the destination host will yield a different value, and we know the data is corrupt and needs to be reset. That's it for this lesson. In this lesson, we discussed Ethernet architecture. We first discussed the oldest Ethernet standard, which uses a physical bus topology with a logical bus topology. Next, we discussed the newer physical star topology with a logical bus and a hub. We also discussed how a physical star can be used with a switch and how that differs from a hub. After that, we covered how the CSMA CD media access method is used to detect collisions. Remember that if you use a switch, this technology isn't required. And we ended this lesson by examining the contents of an Ethernet frame and how the CRC tells us if a packet arrived intact.